Welcome to Networks Professionals.
All right, let's dive in. Today, we are going to pull back the curtain on the numbers that basically run the entire internet. I'm talking about IPv4 addresses. Let's get right into it. You've definitely seen a string of numbers like this somewhere, right? Maybe you were digging around in your Wi-Fi settings, or you saw it printed on the back of your router. But what does it actually mean? Like, what is this digital code really telling our devices? Well, the simplest way to wrap your head around it is to think of it like a digital street address. Seriously, it gives every single device you own, your phone, your laptop, heck, even your smart TV, its own unique location on the network. That way, data knows exactly where it needs to go. Okay, so let's really dig into this whole digital street address idea. We're going to break down exactly how this system makes it possible for, billions of devices to find and talk to each other all across the globe. It all starts with this one number, 32. Yep, that's it. At its absolute core, every single IPv4 address is a 32-bit number. What does that mean? It means it's just a long string of 32 ones and zeros. And that right there, that is the fundamental blueprint for everything else we're about to cover. Okay, so how in the world do we get from a super long, complicated string of ones and zeros to those familiar numbers with the dots that we actually see? Well, let's break down how that 32-bit code is structured to be a little more, human-friendly. Instead of making us look at one giant string of 32 digits, the address is broken up into 4 much more manageable chunks, and they're separated by dots. Each one of those chunks is 8 bits long, and in the networking world, they have a special name. We call them octets. So it's simple math, right? 4 octets, 8 bits each, that gives us our grand total of 32 bits. Now, here's the cool part. With 8 bits of information, you can represent 256 different values. So in computer speak, that means you get all the numbers from 0 all the way up to 255. And this, right here, this is the golden rule. You will never see a number higher than 255 in any of those 4 octets. It's just not possible. So this is really the core of the translation right here. We, the humans, see the easy-to-read dotted decimal version, 192.168.1.1. But when a computer isolates just one of those numbers, let's take 192, it sees something totally different. For a machine, 192 is just that pattern of ones and zeros you see, 11000000. It's like they're speaking a completely different language. And here's the whole picture laid out for us. You can see how each of those decimal numbers from our example address, the 192, the 168, and the 1, each one corresponds to its own unique 8-bit binary pattern. When you string all 4 of those binary patterns together, that's when you get the full, continuous 32-bit number that the network actually understands. Okay, so we've totally cracked the structure. Awesome. But here's the thing. An IP address isn't just one single identifier. It's actually telling us 2 very different things at the exact same time. It's got 2 critical pieces of information packed inside. And this is a really, really crucial point. The first part of the address is called the network ID. Think of that as the street name. Every single device on your home Wi-Fi network shares the same street name. Then the second part is the host ID, and you guessed it, that's like the specific house number. This part has to be totally unique for every single device. So it's like this, same street, but a different house number for everyone. So that leads to a pretty logical question, doesn't it? If it's just one long string of numbers, how does a router or your computer know where the street name part ends and the house number part begins? I mean, where does it draw the line? Well, the answer is this other helper number called a subnet mask. The easiest way to think of it is as another 32-bit number that just acts like a filter or a stencil. It lays right on top of the IP address and basically tells the device, all right, look, this part is the network and this other part is the host. It's the thing that draws that line for us. All right, so we've totally dissected the address. We get the structure, we know about the different parts. But in the real world, where do these numbers actually come from? Like, who or what is handing them out to all our devices? This is a super important concept to get. The IP address your laptop uses to talk to, say, your printer, that's a private address. It only works and only matters inside your local home network. But then your entire network, your whole house, has one single public address that it uses to talk to the rest of the internet. That's the key.
It's why your neighbor's laptop could actually have the exact same private IP as yours, and it's totally fine. But your public addresses, the ones from your internet providers, those have to be 100% unique in the entire world. So, who's in charge of handing out all those private addresses automatically? That's where this amazing little system called DHCP comes into play. It stands for Dynamic Host Configuration Protocol. Basically, when your phone connects to your Wi-Fi, it shouts out to the router, "Hey, I'm here, I need an address." And the router's DHCP service just goes, "No problem, here you go," and assigns one from its available pool. It's literally the reason connecting to a new network is so smooth and seamless. Now look, IPv4 has been around since the pretty early days of the internet. And with all the new technologies coming out all the time, you might be wondering, why do we even still need to understand this pretty old system? It's a fair question. So let's just do a super quick recap of what we've covered. We know an IPv4 address is a 32-bit number structured in 4 octets. We know it has 2 main components, the network ID and the host ID. And the divider that separates them, that's the subnet mask. We also learned about the 2 different types, public and private addresses, and that the allocation is usually handled automatically by DHCP. I mean, these are the absolute core building blocks of how pretty much everything communicates online. And trust me, this isn't just for trivia night. If you want to truly master how data moves across networks, how routing actually works, you absolutely have to understand IPv4. It's still the fundamental language that devices use to speak to each other on the internet. And that brings us to one final really big question. That 32-bit structure of IPv4, it only allows for about 4 billion unique addresses. But today, in our world, there are over 30 billion connected devices. So, if we've run out of addresses, how is the internet still working at all? And what in the world comes next? Now that's a puzzle for another time.
Thanks for watching.